All right, it's officially 2 minutes after the hour, which means it's officially time for us to get going. Thanks everybody for joining us today. My name is Ben Pruden. I lead go-to-market and marketing here at Wherobots. I'm excited to be joined by the team at GeoPostcodes, and we'll be talking about unlocking global raster data population and trend analysis. So before I get started, we would love to learn a little bit of all the folks on the other end of the line, hear a little bit about who you are and what your challenges are with large scale raster data. So in the chat, if you all find the little chat button on the bottom left corner of your screen, we'd love to see a message from you. Let us know who you are, where you're from, and what sort of challenges you might be having with large-scale raster data analysis. We'd love to learn a little bit more about those things as we get going. So let's hear some folks from the chat as we get going. I'll go ahead and just forward to the next slide, but I do want to see what we can hear from folks. There was the chat not fully working. Yeah. It may not be fully enabled actually. You can put it also in the Q&A section, which is another option here if you want to just answer in the questions and answers section who you are. That would work too. Okay. We're gonna keep going. We do have some polls that'll be going as we go through the webinar today. So you'll be able to review them and review the answers as we go through them. The slides will advance throughout the talk, and we'll have the recording up for you in the next 24 hours. And I do actually, since I didn't walk through the agenda, I'll go back to that just briefly. So we'll start off with some intros for folks here. Then we'll kind of go into population data overview, some common use cases for population data, and then we'll talk about our implementation with GeoPostcodes and the outcomes they were able to achieve, the challenges that we experienced along the way, and then the solution. All right. So as we get going here, I'll kick it over to Jerome. Jerome, you want to introduce yourself?
Sure. Thanks a lot. Nice to meet everyone. Thanks for attending this session. So I'm Jerome, the head of products of GeoPostcodes, and I'll give a short intro of GeoPostcodes in a minute.
Wonderful. My name is Daniel Smith. I'm the senior solutions architect. I'm coming from Wherobots, and I will tell you a little bit more about our solution here in just a few minutes.
All right, cool. So let's go ahead.
Awesome. So let's introduce GeoPostcodes. So we're a Belgian company. We've been providing global location data to enterprises for 15 years, and we have 3 categories of products: address data, map data, and demographic data. So our address data consists in standardized tables containing addresses and including up-to-date street names and postal codes, but also a lot of related information such as administrative divisions, time zones, the closest UNO codes, or coordinates. So of course, as we have coordinates, you can display that on a map, but we also have, let's say, purely map products containing the polygons covered by each zip code, so the zip code areas, and also the boundaries of each administrative division. And finally, we have demographic data, which is going to be the focus of this session with our population database. So we do all that for the whole world, which is 247 countries, and common use cases for our data are address capture, business intelligence, master data management, logistics and supply chain monitoring and optimization, market research, and visualization. Over to you, Daniel.
Wherobots, a little bit more about Wherobots. Wherobots is the SaaS offering of Apache Sedona. So the original creators of Apache Sedona, the cluster computing geospatial library, formerly known as GeoSpark, have stood up Wherobots in order to bring the benefits of cluster computing to all of you as a managed service. The benefits of Wherobots are really like its scalability, its performance. We offer a lot of additional storage capability, modern data lake, cloud native capabilities. One of the major benefits of using Wherobots is its open core technology. And so you're able to lift and shift all of your Apache Sedona code, run it in Wherobots with little to no modification. Next slide. Our performance benefits are really kind of speak for themselves. You guys can check out our blogs on these. Over Apache Sedona, our implementation and our engine offers a 20 to 60% increase in performance compared to BigQuery and other offerings like Snowflake. We regularly come in at 10 to 60% faster in geospatial queries, not just joins, but also data creation. So like computing the intersections, computing for any polygons, those types of things. Next slide. So yeah, we have this is our first poll. And so we're curious how you folks handle large-scale data aggregation in your organization. So maybe this might be joining large-scale vector and raster data together. This might be merging multiple levels of polygons, or even integrating multiple rasters together. And so the poll should be open now, and you guys can kind of select which one of these is your main handler for dealing with these large-scale data sets.
All right, just open the poll, so everybody should have it now.
Right. I think over to you, Jerome, to talk about the implementation that you guys have built.
Well, let's give it a minute. I see a bunch of answers coming into the poll here. So looks like 17, 18 of the participants have answered. So let's let a few more folks provide their responses as we go here. I'd love to see us get past 70 or so percent. We're at 25, 50, 60%. So far, it's almost a tie between how do you handle large-scale raster data aggregation in your organization. We've got in-house systems, third-party tools almost tied, manual processes at 10%. So in-house system and third-party tools at 33 and 30%, manual processes at 13%, and still exploring options at 23%. So far at 68% of the participants. One more answer coming in. It's kind of about still the same though. So very cool. All right. Well, we'll make sure and share those results at the end though, but we're about tied. In-house systems, third-party tools are tied for almost first, manual processes third, last, and then still exploring options at 26%. Okay, back over to you, Jerome.
Thanks a lot. So let's talk about population. So our population data contains historical, present, and future population estimates for all countries and for each administrative division and each zip code area. So how do we build it? You can look at the nice GIF on the right. So we use reliable raster population, which you see on the left side of the animation. And we overlay our created boundaries data, which you see on the right side, and it's gonna turn red. And so you see we put, let's say, the two data sources on top of each other. And once that is done, we aggregate the raster values falling within each polygon. So we do that for each zip code area. We do that for the administrative divisions as well. And there we only compute the population for the most granular administrative divisions. And then once we have that, we can propagate the values up to the less granular divisions. I'm going to come back to that in a few minutes. So we do that for the whole world for 12 different years in the past, present, and future. And the results is population values, density, and trends, as I said, for each administrative division and each zip code area. So we can move to the next slide, which is actually another question for you, which is what other data sets would you want to be linked to administrative division data on your site?
All right, so this is a short answer question, which means you can type your short answer into the poll results. And this time I will share the results back with everybody so you can see what your answers are as opposed to giving you the percentages. So we got one person that's bravely put an answer. Now two, good. Okay, got some more rolling in. Awesome. I feel like we should have some of those, music from The Price is Right or something. All right, now we got some more answers rolling in. 6 answers coming in. Keep going. Let's get more than 6. Here we go. 7. Cool. What data sets would you want to have available in your administrative data is the question. We'll leave it open for another 20 seconds. We got nine responses, which is pretty good. Let's see what those are all about. All right, we'll go ahead and end poll, and let me share the results. So, whoops, didn't mean to do that. Well, let me come back to this. Hold on. Poll results. What other data would you like to have in here? I'm going to just stop sharing for a second here, folks, so that we can pull this out the right way. We'll view the details. So I'll just share what people said overall. So household income, business and commercial, number of business types, demographics, climate and physical risks, economic data, official languages, time series data, and amenities. So that's interesting.
Yeah.
Very cool.
Very interesting. Thanks a lot. Yeah, cool to discuss use cases for that with you and what we can do in the future.
Exactly. And apologies for the little bit of a fumble there with the sharing. All right. So I'll let you go ahead, Jerome.
Thanks. Yeah, so some use cases for population data. Of course, first is territory mapping. So knowing where people live can help you distribute your sales force, decide where to open the next shop or the next warehouse. Another example is ad targeting. Of course, you can also optimize your marketing efforts with accurate population knowledge. And last but not least, population trends play a critical role in real estate, for instance. So, of course, knowing where the population is going to grow can lead to significant business opportunities there as well. So we can move to the next slide, which is going a bit deeper in the implementation of the method to compute population for zip code areas and administrative divisions. So as we already explained, we want to aggregate raster data with boundaries data. And there's actually a core plugin in QGIS to do that, which is called zonal statistics. And what we did is that we Dockerized QGIS, so we can deploy a headless version of QGIS without the graphical interface to any server. And the Docker container can, of course, access both the raster data and our boundaries data from a PostgreSQL database. As we said, we only compute the zonal statistics for the zip code areas and the most granular administrative levels. And I'm going to illustrate that with the figure on the right. You've all recognized the beautiful state of Delaware, which is very useful here, not only because it's the state with the smallest number of subdivisions in the US, but also it has a vertical shape which fits nicely in the slide. So it only has 3 subdivisions, three counties, which are Newcastle, Kent, and Sussex. So what we did there is compute the population for those most granular levels, so the counties. And so roughly we have 650,000 people living in Newcastle, 200,000 living in Kent, and 250 living in Sussex. So now if you want to know the global population living in the total population living in Delaware, of course, you could still run the spatial computations and leverage the zonal statistics, but that's not necessary here because you have the values for the 3 subdivisions, and you can just sum those up to get the value for the Delaware population, which in this case is roughly 1.1 million inhabitants. So that's it for the let's say, original implementation. And of course, we wanted to validate the method. And to do that, we compared our results with official census data for several countries. As you can see here, the correlation coefficients are really, really high. So it's giving a lot of credit to the method. We see we're nicely following the trends that are published in official census. So it's generally validating the whole methodology, and also the aggregation to upper levels is working fully and perfectly. And so once we had that, of course, the only thing to do was to deploy that to the whole world. And so you can go to the next slide. Yeah. So we deployed that to the whole world, which is again 247 countries. We have 12 different rasters, because we have 12 different years with population data. We aggregate that over high resolution boundaries from both zip code areas and administrative divisions. And all that together led to a quite high computational load on our regular infrastructure. It actually took almost 40 days to produce all those figures, which of course has some, is creating some side problems as well. Well, the first thing is it delayed a bit the product launch, but also we had to closely monitor the progress of the computations. And luckily it didn't happen, but it would have been very annoying if we had to restart the computations for any reason, like there was a bug or there is an update in the underlying data source. You're losing a lot of days if that's happening. So realizing that, we started looking for a more efficient infrastructure, and we got strongly attracted to the Wherobots approach to do that. And so before I hand over to Daniel for that part of the solution, I think we have another poll, another question. So the question is, what's your biggest concern when it comes to data aggregation? Could be time, or maybe diverse data formats, or you need to aggregate different data sources, not there are discrepancies between them, or maybe something else. So please let us know.
All right, we've got the poll open. Thank you all for jumping in. We've got responses coming in quickly this time. So we should be able to do this relatively easily. Looks like discrepancies between data sources is really the consistent area of challenge. Values computed differently, different granularity is a consistent challenge for folks. Followed by diverse data formats and time are the other two that are coming through. And I know you can't put other responses in the chat because we didn't quite get the chat working. So if you wanted to put those other responses in the Q&A, again, you can do that instead. All right, I think we got a good group of responses. I'll go ahead and share the results with everybody. So again, we got discrepancies between data sources, 71%, diverse data formats, time, and then others as final. So definitely discrepancies between data sources and values is the consistent challenge for folks. All right, go back. And I think those are the last of our polls here today. So I'll pass it over to Daniel to talk a little bit about the solution.
Wonderful. Thank you. I want to thank GeoPostcodes for bringing this problem to us. I mean, this is a super interesting global scale problem that Wherobots is perfectly suited to answer. So when we started to dig into the problem here and try to figure out a more efficient and a more practical way to do this, we really landed on kind of using three main pieces of our technology. So the first is the leveraging Parquet format. So leveraging the columnar data store and the partitioning of that data. All of this data was brought into Wherobots DB, which is an Iceberg-esque type of data store. It is extending Iceberg to include native first-class geospatial data as a data type. We brought that in, and we used our concepts of out-DB raster. So rather than storing all of our rasters as uncompressed values within our database, we could keep them off to the side and use out DB raster functionality. And then all of the analysis was done with pure spatial SQL. And so rather than having a convoluted pipeline or a long Python script, like all of this was easily expressible using SQL. We're going to look at the code in a second, but before we do that, we're going to take a look at some of the results. Mr. Ben, thank you. And we were really impressed. We can see the multiplier factor on the right side, looking at the zip code counts, how many there were, what the runtime was previously per country, and kind of what we did here. And we can see very quickly that like using the Wherobots platform, using this more advanced technology, this newer cloud native distributed system, we're seeing gains up to 135x, right? Like this drives down the processing time, allows GeoPostcodes to make additional edits and make additional changes, integrate new data sets, build new data sources, and bring it all together and be able to deliver these products in a time scale that is much more reasonable, much more performant. Along with all of this, rather than having kind of this headless implementation where you're not really sure and you're really worried about some of the other pieces that can go wrong, this system churns through the data at such a scale and such a clip that if there is an issue, it is quickly brought to the surface, and you can make adjustments from there. I wanted to we'll talk a little bit about the second one here, Russia. This time, like while we still see a gigantic performance, it stands out in our test set as being an extremely large outlier. And I want to talk a bit about that in a second. But I think that we're going to do a quick walkthrough of some of the code so we can explain a little bit more about the data, and we can show you guys some of the actual code that went through to process this and a couple of the processing tricks that we deployed here. Give me a second to share my screen. We all seeing my my notebook here? Awesome. Okay, so one of the main points of interface for Wherobots is using Jupyter notebooks. We also offer other Python APIs. We have a TypeScript API for interacting in more web-based applications, and various other contact surfaces. And so if you want to learn more about those, feel free to reach out or to check the Wherobots documentation. Be happy to help you guys get set up and start accessing some of these distributed computing clusters. So a little bit about the inputs. Originally, this was 171 Parquet files. This is the partitioning by country. This was about 4.5 gigabytes and just over 650,000 polygons. These are very complex polygons. When you consider the borders of places like England or Russia, as we'll see in a second, there are many vertices and many polygons that need to be computed against. As Jerome mentioned, what we're actually using is the global human sediment population data for 12 years. And so this isn't just one raster overlay. This is actually 12 concurrent overlays every 5 years, going from 1975 to 2030. So we have some of the prediction values here. And we can see the size of these individual rasters here. In total, this is about 106 gigabytes worth of raster data. This is 100-meter resolution, and it's provided at a global scale. A little bit about working with Wherobots and working with Sedona and working with Spark in general is building the context here. I'm going to kind of pass over some of this setup code, and we can look at the actual processing pieces here. The first step, very straightforward. We directly support cloud native formats like GeoParquet. And so bringing this in and setting this up is just as simple as saying, read format, load our data source. And we're pulling it directly from our S3 bucket here. Some basic information, the zip boundaries have this type of schema here, geometry and additional bounding box. The additional boundary data also that we imported here, very straightforward. We have our geometry, we have our ISO code, zip codes, and so on and so forth. The administrative boundaries as well. So a couple of additional features here. The type of administrative level, like Jerome noted, they have multiple levels of administrative boundaries. And so they go from, the most granular that each country has up to the very high level. And so you're able to view and render all of this or analyze it as well. So as we said before, like we bring all of this data in. And so what we actually do, there's a This is the first part of our optimization here, is that we actually take this data and we repartition it. And so we don't have it just as the original like countries. We actually create 1,000 partitions in memory here, and then we write it to our database. So we're actually storing this data in our Havasu format. Additionally, we create a spatial index on here. This kind of reorders our data, not so much for the spatial joining part, but before the axis. Do that both times. Again, we repartition our zip and our administrative boundaries and build the same spatial index here. Reading the raster data. So I mentioned that we use OutDB rasters within Wherobots, and so here we're just pointing. Oh, good. Okay, good. Visual glitch on my side. And so we support OutDB rasters, and rather than bringing all of this data in, all of the individual TIFF files, we just point to it. And so we're kind of just saying, hey, these are the raster files off to the side. And like we said, they're very large. So these are global scale individual rasters. And so the first step that we do to kind of optimize this is we tile it. And this isn't like a tile on disk. This is more of like a concept of a tile, right? And so you end up identifying these 256 by 256 pixel size rasters, and we kind of end up working with those footprints. This allows us to more evenly distribute the load, not having to send the entire raster out to all of the nodes that we use to process this. We can see here that these get loaded as an OutDB raster. Here, all right. Right. So then the main, like this is kind of it. So the first optimization that we really were looking at is doing a partitioning. And so within QGIS, like that single node, kind of single core machine is really kind of accessing all of this data simultaneously, right, within one instance. Rather than doing that, Sedona and Spark is a distributed cluster computing system. So we're able to take individual pieces of our data set, both the raster and the vector, and send that out to different cores for the actual processing. At the end of it, all of the results are brought back together and rendered and stored, however, in whatever format you're looking for. In this case, we actually end up writing it out to GeoParquet. And so the first step in this process is really a tile matching. And so, like I said, rather than sending the entire image out to any of the nodes, we actually do the tiling, and then we match those tiles to our individual zip codes. And so when we send this out to processing, the tiles that intersect any of our boundaries, that is all that is sent, right? And so the pixels themselves aren't actually materialized until we need to run our zonal statistics. And so thinking about this, we initially ran this, and our test for the United States ran in about 30 minutes. So no optimizations, just bringing in the Parquet files as they were, running basic code without some of these optimizations in here. Took about 30 minutes. With repartitioning, and then we kind of had this realization that there's actually no data value. There's no data value in these rasters, which, okay, that makes sense. It's a global raster. You have zero population here. But it kind of dawned on us that you actually don't need to materialize any of these zero cell rasters, right? Like we see a tremendous performance increase when we don't have to materialize data that means, zero people. And so dynamically for each tile, we actually set this no data value to 0. This reduces the number of actual pixels that need to be retrieved from our data set to do that zonal statistic. This is probably one of the biggest increases in performance that we saw. This took the United States down from a 30-minute runtime down to about 5 minutes. I think that that's kind of the main chunk there. After we kind of run all this, again, this is run for all 12. And so this isn't, run one layer, run two, like we're sending all of the tiles for all 12 rasters simultaneously. What we end up needing to do is a pivot table. And so we can just kind of rotate these columns over so that we have the individual zip code ID here, and then the population for all of the subsequent years. This is really where kind of the whole rubber meets the road, right? Spark, if you're not aware, is lazy. And so it won't actually compute these things until you need it to, right? So like this section of code here doing the pivot table, it says the wall time is 9.48 milliseconds. This isn't actually computing the pivot table at this point. We have to do something with the data, show it, try to count it, do some other function that forces the system to materialize the data. In this case, rather than counting or rather than showing any results, we're actually saving it all of the way out. So generating the final data product, not an intermediate product, not like a temporary view, but like the final deliverable product. And that is where we kind of see this here. And we see our individual runtimes per country. Again, like we see Russia as this gigantic outlier here in terms of ours, 1 hour and 6 minutes. It's on the scale with Saudi Arabia, and a third of what Japan has that's still coming in at 3 minutes. I think if we switch back over to the slide, we can kind of take a look at why Russia was such an outlier. Stop sharing.
All right, I'll pull up the slides just a second.
Yes, sir.
There you
go. So really, it's a function of not just the spatial extent. I mean, Russia is the largest east-west running country, but there is such a wide variety in the shapes and sizes of these, and so our partitioning strategy didn't work out particularly well for this country. We can develop additional partitioning strategies based on country, but with such a wide variety of space and a wide variety of sizes, our partitioning strategies, frankly, was not the best. And so we've started to look at other ways that we can do like country-based partitioning, or additional ideas that we have and that we're thinking about are splitting these up so that we have a more uniform distribution of polygons, and that we could like bring those all back together. So taking a rather large polygon like you see in this main picture here, subdividing it up into something a little bit more reasonable to then distribute. So there's fewer tiles to go with it, there's fewer computations, and then bringing that all back together in the same type of summary statistic that you would use for doing any of this. We can go to the next slide. Yeah, and so this is kind of like the main way that we went about this, right? We went from a multi-day runtime, 30, 40 days worth of processing that you can't really check out, that you can't really see intermediate processes. As Jerome said, if there was a glitch or a problem with the data or the system, it would have necessitated rerunning the data. Possibly from the very beginning, if we didn't have reasonable checkpoints built in, they could have very easily been in a situation where having to rerun a 40-day process really would push back their delivery time, really hamper their go-to-market activities and their growth. I think from there, we talked about how Wherobots uses their OutDB Raster technology, the distributed system. We talked a little bit about the very specific optimizations, repartitioning strategy, the kind of the domain knowledge of removing zero-value pixels. We talked a bit about some of the challenges that we have. So like Russia example, again, very large polygons, very diverse set of size polygons, and just a very large spatial extent. That's kind of the recap there. Ben?
We have a number of questions in the Q&A, so I think we can switch to that. Thank you all for all the comments and the engagement. So we'll start off with Naresh from Singapore. Hey, Naresh, if you're still on. So the question was, how do we generate a comprehensive and accurate population data for countries which are densely populated where vector data isn't present? And then how do we use raster dataset to derive the population data for countries like India and Indonesia? Jerome, you want to, that one sounds like one for you.
Yeah, thanks a lot. So yeah, good question. Of course, in some, countries are different and density is different, but most countries still run census. So you have some kind of official data about population, which is usually, they run census at some granular level. And then there are some public institutions trying to also make models out of that. And the source we used is actually leveraging censuses and trying to do forecast. And of course, it's using AI and prediction models, which then adapt to the local context and don't deal with the, I don't know, Singapore the same way as the desert. Yeah, we do leverage sources that we can trust, and we've also shown that we validated that afterwards, also comparing with the census data. But that's not the process we do. We confirm the validity of the sources, and there are a lot of public institutions working on that. So both national and European Commission. So the source we use is from the European Commission. There's a lot of research going into that to try to have accurate figures, both present and predictions, in all the countries. So I hope this answers the question.
Awesome. Thank you, John. I'll go to the next question from Krishna. So Krishna asks, what are the most innovative use cases for geospatial data analytics and AI, finance, supply chain, healthcare, and insurance sectors? Very broad. Daniel, what do you think? I'd love your thoughts here.
Gosh, I think, a lot of, with regards to finance, I think there's a lot to be done within like, I don't deal with a lot of finance. I think that like one of the main use cases that I've seen with geospatial and AI and ML is like predicting money conversions. And so like when and where, like where and when you convert money from one currency to another actually has a big impact on the bottom line. So like throughout the day, the comparison of $2, right? Like it changes like what the exchange rate is. And so I've seen some like pretty amazing things where they've optimized that both spatially and temporally to have essentially, zero input increase in profits. Like those types of things. Supply chain, I think, predicting, again, like the predictive side of AI and ML is really where you're looking at here. And so things like predicting road risk, I think we've got a great demo and a use case on road risk in Europe that you can check out. Healthcare, predicting future state of, I think we've seen great work with overdoses and drug use within the United States. There have been some really big improvements there. Predicting healthcare outcomes is often a function of your location and like what you have available to you. So, the number of doctors that are nearby, your ability to reach these places. I think the insurance sector is, a huge sector for geospatial and AI and ML, right? Like any number of factors influence not only your risk level, but also like, how much should be insured for. If you look at Florida, there's tons of discussions about how insurance companies in Florida are either pulling out of that market or really leaning in, knowing that, the future with global climate change is going to have a severe impact on human and environment and natural resources.
Yeah, I'll echo the couple of those really quick, just for the sake of completeness. I actually joined there's a really interesting spatial finance workshop / session I went to a couple weeks back, right after Phosphor G North America, and similar, like for spatial finance in particular, it's all about time to answer. If you can get the results to a question more quickly than somebody else, then you can profit from it, basically. So how quickly can you ultimately provide a response? And then similarly, like for insurance, it's all about catastrophic risk management and understanding where those risks are going to be coming from, and how to get ahead of them, how to appropriately price for them. So all right, we have a question from Matt. Have you tried an area weighted partition and noticed any performance difference somewhere like Russia with a lot of variation and polygon size?
Matt, it's nice to hear you. I'm glad you joined the conference. I know Matt from previous employment. Actually, we didn't. I think that's one of the things that we do want to try is that subsetting of space. So taking these large polygons and just arbitrarily splitting them. There's some really great functions that we have that allow you to just kind of slice and dice and subset these into much more uniform size polygons. And so I think that, yeah, we definitely want to try some of these strategies. We computed this at the zip code level for a few select areas. From here, we're going to start developing and testing a more comprehensive strategy for doing it with zip codes, with all the base administrative levels. We actually need to compute those separately because they don't nest properly, right? We talk about zip codes and my issue with zip codes, but that's a whole different story. But yeah, I think those like the size partitioning, splitting them up into smaller polygons is probably going to give us some performance increases as well. I think we'll be talking about this. We hope to get that done for the Spatial Data Science Conference. And so I believe Jerome and I are presenting at the Spatial Data Science Conference in New York in the middle of October. And we hope to have some of these additional improvements kind of documented and run by them.
Cool. All right. Well, one last question. I think also, Daniel, for you. In your spatial index, you seem to be using Hilbert curves. Have you experimented with other algorithms that might affect the performance gains? Not
as such. Using the Hilbert curve, that spatial indexing is something that we've developed and was developed internally. And so that's kind of the main index that we're using here. And again, that's a space filling curve for those who aren't familiar with Hilbert. It's a space filling curve that allows us to like resort and reorder this data. And so I think that for the most part, this would help with like access. It's not going to give us much improvement with the actual computation. And so that's more about like the spatial filter pushdown and being able to pull stuff out of storage in a more efficient manner rather than doing spatial filling.
And Jordan, you raised your hand, so I went ahead and allow you to talk. So go ahead. Anything else you want to add?
No. Thanks.
Okay. Sure thing. Cool. All right. Well, I think we've hit all of our topics for today. So we're really grateful for all the participants that joined us, folks from pretty much all over the world. So little glitches here and there with the chat. Sorry about that. Hopefully we did get it opened up for everybody towards the end there. But we really appreciate you all joining and engaging. If you want to follow up with us, you can reach out to Daniel directly at Wherobots, daniel@wherobots.com, or if you want to just have a broader sort of inquiry or chat with us, you can send a note to info@Wherobots or just fill out our contact form on our website. And then for Julian, Jerome, Jerome, you can reach out to directly at jerome@geopostcodes.com. So again, thanks everybody. Really appreciate you all joining us today, and thanks for your questions. Some of them trickier than others, and I really appreciate the time. So with no further ado, I think we're gonna wrap it up. Daniel, Jerome, you want to last farewell?
All right. Thank you all so much for attending.
Thanks a lot. I'll see you soon, hopefully.
All right. Thanks everybody. Take care.
Bye. Take care.